Hello everyone, welcome to Augment Tech. We empower engineers for better career opportunities. Today, in this session, we will learn about ultrasonic flaw detector. So, let's start. After the end of this tutorial, you would be able to understand ultrasonic flaw detector, understand A scan, understand B scan, understand C scan, and you will also understand D meter, that is the thickness gauge. So, we will begin with ultrasonic flaw detector. Ultrasonic flaw detector are devices which are used on standard engineering material to find hidden cracks, voids, porosity, inclusion, and other similar discontinuities. Modern ultrasonic flaw detectors are a small, portable, microprocessor-based instrument suitable for both shop and in-field use. A typical flaw detector is shown here. They generate and display an ultrasonic waveform that is interpreted by a trained operator, often with the aid of analysis software to locate and categorize flaws in a test piece. Ultrasonic flaw detector provide unmatched capabilities for locating discontinuities and other flaws. A wide range of software option is available for enhanced flaw detector inspection. It offers a wide range of measurement features and application-specific options for flaw detection application that include the location and sizing of hidden cracks, voids, disband, and other similar discontinuities in weld, forgings, turbine, and other structural component. They will typically include an ultrasonic pulsar receiver, hardware and software for signal capture and analysis, a waveform display, and a data logging module. The pulsar receiver section is the ultrasonic front end of the flaw detector. It provides an excitation pulse to drive the transducer and amplification and filtering of the returning echoes. The display may be a CRT, a liquid crystal, or an electroluminescent display. Internal data loggers can be used to record full waveform and set up information associated with each test, if required, for documentation purposes or selected information like echo amplitude, depth or distance reading, or presence or absence of alarm conditions. Pulse amplitude, shape, and damping can be controlled to optimize transducer performance, and receiver gain and bandwidth can be adjusted to optimize signal to noise ratio. Modern flaw detectors typically capture a waveform digitally and then perform various measurement and analysis function on it. A clock or timer will be used to synchronize transducer pulses and provide distance calibration. Signal processing may be as simple as generation of a waveform display that shows signal amplitude versus time on a calibrated scale, or it can be as complex as sophisticated digital processing algorithm that incorporate distance amplitude correction and trigonometric calculations for angled sound path. Alarm gates are often employed to monitor signal levels at selected points in the wave train to flag echoes from flaws. We can classify the scanning methods of an ultrasonic flaw detector into three types: A scan, B scan, and C scan. All these three modes of scanning are obtained with respect to the pulses of ultrasound transmitted into and received from the specimen. First, we will learn about A scan. A scan stands for Amplitude Mode Display. The most basic presentation of ultrasonic waveform data is in the form of a scan or waveform display, in which echo amplitude and transit time are plotted on a small grid. A scan display gives only one dimensional information about the given specimen. It gives only one-dimensional information about the given specimen. In this, a single transducer is used to transmit and receive the pulses from the specimen. The vertical axis represents amplitude and the horizontal axis represents time. A typical A-scan display is shown here. A-scan display indicates discontinuity's depth in the x-axis and the amplitude of the sound reflection from the discontinuity in the y-axis, which is a relative measure of the size of the discontinuity. In ultrasonic flaw detector, A-scan method is used to detect the position and size of the flaw. Another way of presenting this information is by B-scan. B-scan or brightness mode display gives a two-dimensional image. The principle of the B-scan is same as that of A-scan, except with a small difference. Here in the B-scan, the transducer can be moved rather than keeping in a fixed position. This representation gives the side view of the material being tested. Shown here is a display of a B-scan. It plots the depth of reflectors with respect to their linear position. It indicates discontinuity's length in x-axis and depth in the y-axis. The thickness is plotted as a function of time or position, while the transducer is scanned along the path to provide its depth profile. Correlating the ultrasonic data with actual transducer position allows a proportional view to be plotted and allows the ability to correlate and track data to specific area of the part being inspected. The third mode is C-scan. It is also called time motion mode or C-scan display mode. This combines the feature of both A-scan as well as B-scan. C-scan displays the plane view of the material being tested. The C-scan is used in corrosion mapping and by techniques other than just ultrasonic. It is not limited to showing amplitude, but it is also used to display changes in measured wall thickness or qualitative measurement in the extent of corrosion. The only disadvantage of C-scan is that it will not provide the depth of discontinuities. C-scan refers to the image produced when the data collected from an ultrasonic inspection is plotted on the plan view of the component. It is the image of the results of an ultrasonic examination showing a cross-section of the test object parallel to the scanning surface. However, the C-scan does not have to be single cross-section, but often shows a combination of measurement obtained through the whole thickness. Controls. Now, we will look at some of the basic control of flaw detector. A typical ultrasonic flaw detector is shown here. First, we will understand about sweep control. This control is used to set the horizontal line, that is, the time-based line of the CRT, to represent a given thickness of a given material. Next is pulsar control. This control is used to activate the transducer. The electric pulses emitted by the pulsar excite the piezoelectric crystal to generate ultrasonic pulses. Next is clock control. This control activates the sweep circuit and the pulsar at the same time. Clock circuit controls the pulse repetition rate. The number of times the pulsar emitted is called the pulse repetition frequency or the pulse repetition rate. Normally, a pulse repetition frequency of 100 to 1000 per second is employed. The last one is receiver or amplifier control. The amplifier amplifies the received signal from the transducer. All this control and the working of ultrasonic flaw detector will be explained in detail in the video attached with this course. Now we will look at the digital thickness gauge or D meter. D meters or digital thickness gauge instrument provide the user with a digital numeric readout. They are designed primarily for corrosion or erosion inspection application. Some instruments provide the user with both a digital readout and a display of the signal. This is the most common type of ultrasonic device. It is only used to measure the wall thickness of a pipe or any other pressure vessel. These are generally used in pipeline inspection. They are used for the measurement of wall thickness of material such as steel, plastic, and more using ultrasonic technology. You can see in the given image that a D meter is being used to check the wall thickness of a pipe. These are ideal for measuring the effect of corrosion or erosion on tanks, pipes, or any structure where access is limited to only one side. Now there are higher model available such as UTGM through paint models, which measures the metal thickness of a painted structure without having to remove the coating. So that was all about ultrasonic flaw detector, A scan mode, B scan mode, C scan mode, and D meter. Hope you enjoyed the session. See you again in the next one.